Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue our discussion on supersonic and hypersonic shock interactions and hypersonic flight trajectories, the basic concepts. So, you recall in the last lecture, we initiated the discussion on shock-shock interaction. This time, we are going to complete it. Followed by that, we will discuss about shock wave boundary layer interaction, lifting and ballistic entry of hypersonic vehicles and hypersonic flight paths during atmospheric entry. We have qualitative sketches of the 6 different shock-shock interaction patterns provided below, and the region within which the incident shock meets the cowl shock is indicated in the diagram on the left. So, we have made an enlarged view of the blunt leading edge, which we were considering as the engine cowl of a scramjet engine. It could be occurring in other situations too on hypersonic vehicles, and you notice that the bow shock stands here ahead of the blunt leading edge, and additionally 6 sectors with Roman numbers have been marked. And one particular type of interaction also has been sketched here. We remember that pressure deflection diagram was discussed in the last lecture, and pressure deflection diagram for intersection of 2 oblique shocks of opposite families was also discussed. That applies to type 1 interaction, which is sketched on the left. This is the one we are referring to. I hope you recall the similarity between the example that we discussed in the context of pressure deflection diagram at that time. Can similar diagrams be drawn for the remaining types of shock-shock interactions, which we will be discussing subsequently? That is something that you need to explore later on, and this particular reference will go a long way to help you out. Type 1 interaction. We already saw a sketch of it on the previous slide. We see 2 straight oblique shocks of opposite families. The left running shock IS intersects the right running shock BS. By now, you should be familiar with the nomenclature, and this results in 2 transmitted shocks and a slip line trailing downstream from the intersection point. So, this is the slip line we are talking about. The flow is locally supersonic everywhere in this pattern. This is something that you need to note. Type 2, here the shock IS impinges on the bow shock BS at a location just downstream of the sonic point. You may have noticed that there are 2 sonic points here located on the upper and lower side of the body. For a perfectly symmetric body, they would be exactly at the same angular orientations above and below the central line. The curved bow shock is stronger at this location. The local flow Mach number is lower. The type 1 interaction pattern cannot occur because the flow deflection angles exceed the maximum allowable limits by straight oblique shock theory. Therefore, the 2 intersecting shocks are connected by a nearly normal shock, which is a Mach reflection. This is something that you need to explore on your own. I am leaving a small homework for you. An embedded region of subsonic flow trails downstream from the interaction region. This is the region we are talking about. Therefore, it is evident that type 2 shock-shock interaction pattern is a mixed subsonic supersonic flow field, unlike the type 1 where it was everywhere supersonic. We move to type 3. It occurs when the shock IS impinges on the bow shock BS at a location just upstream of the sonic point behind shock BS. Here the flow behind the shock is locally subsonic. However, it is a fairly high subsonic Mach number, not far from sonic condition. A slip line trails downstream from the intersection point and impinges on the body. This slip line separates the local subsonic flow above it, that is the one, from the locally supersonic flow behind it. So, you have an acceleration. The locally supersonic flow below the slip line is turned by the body surface through a rather complex wave pattern. So, without bothering too much about the complexities of the wave pattern, we just try to get a bigger picture of how the interaction has happened in this region and how different it was from type 1 and type 2 in terms of the mixed Mach number ranges and the flow features broadly. Coming to type 4, which we had mentioned earlier also in the previous lecture, because of its enormous significance in these kind of interactions, it is the type 4. It occurs when the shock IS impinges on the stronger part of the bow shock BS, stronger in the sense regions where you have a subsonic flow behind the bow shock near to the stagnation region at a location usually far upstream of the sonic point. In this region, the turning angle of the flow by the body is too large for the supersonic flow to be deflected downstream through an attached shock. This was possible for type 3 interaction, though. Behind the impinging point of the impinging shock, a supersonic jet is formed. So, we are talking about this zone. It is bounded on both sides by slip lines which are marked as SL, and they separate the supersonic and subsonic regions. So, it is essentially that narrow region which contains the supersonic feature. The supersonic jet penetrates the flow field, essentially the subsonic neighborhood, towards the body and terminates in a normal shock which is marked as NS at the end of that jet in this part close to the body surface. There are strong spikes in the pressure distribution and the local aerodynamic heating on the body surface in this region, where the normal shock at the end of the supersonic jet forms close to the body. Pressure and heating rates up to few tens of times of non-interacting case have been measured and computed. The local heat transfer rates are nearly proportional to the pressure. Therefore, peaks of pressure would therefore be always accompanied by peaks of aerodynamic heating due to high heat transfer rates. These pressure and heat transfer peaks make the type 4 shock interaction a very serious matter for hypersonic vehicle design. Incidentally, at the design condition, the inlet bow shock emanating from the vehicle nose is going to impinge on the engine cowl. We mentioned earlier, this is also essential to keep the flow confined and make it enter the engine to prevent spillage losses, and if that is to happen from the engine performance point of view, then accompanying that there is every chance that type 4 interaction will occur at the engine cowl, and therefore, we have to live with this aerodynamic complication. Type 4 interaction flow field is also highly unsteady. The interaction frequencies can vary from 1 kilohertz to several tens of kilohertz. This could be detrimental for the structure, which could fatigue more rapidly under the unsteady aerothermal environment. Coming to type 5, this shock-shock interaction occurs when impinging shock and bow shock are of the same family. They are both left running shock waves in this case. The impinging point is just downstream of the sonic point behind the bow shock. As a consequence, because of the symmetry, type 5 and type 2 are very similar in nature. In the type 5 interaction, the two intersecting shocks are connected by a nearly normal shock, which is formed here. This produces a Mach reflection like pattern in type 2. An embedded subsonic region forms downstream from the interaction region. There is often a very thin supersonic jet which is formed at the interface, but it acts more like a slip line. Finally, we come to type 6, which involves two intersecting left running shocks. The impingement point is far downstream of the sonic point, the upper sonic point, that is. This is analogous to type 1 interaction. Here, two shock waves of the same family intersect at a point, coalescing into a single transmitted shock and a slip line trailing downstream from the intersection point. So, we had a broad look at the flow features involved in shock-shock interactions, the 6 types which have been categorized by Edney. We next move on to a discussion on shock boundary layer interaction. Let us see what that is all about. There are various flow regimes in the compressible flows, and if you look at the lower Mach number regimes, we start from compressible subsonic flows, moving on to transonic, supersonic and hypersonic. If you were to consider flow past an airfoil, which is usually considered to be a more efficient geometry for flying at subsonic speeds, as long as the free stream Mach number is around confined to around 0.7, the flow remains subsonic over the entire airfoil, and local Mach number over the airfoil varies as a function of its shape and could well exceed the free stream Mach number in regions of high acceleration, especially on the upper surface because of the camber, and this is more so in case of thick airfoils. From there comes the definition of critical Mach number, which is the free stream Mach number at which sonic flow is first achieved on the airfoil surface. As the free stream Mach number increases further, a local pocket of supersonic flow is formed on the upper surface of the airfoil. This pocket is terminated with a shock wave. Gradually, a supersonic pocket emerges on the lower surface as well, and this kind of flow is termed as a transonic flow, which happens close to Mach 1 condition. The value of m infinity beyond critical Mach number at which sudden increase in drag starts is called as the drag divergence Mach number. Beyond drag divergence Mach number, the drag coefficient will suddenly rise up by a factor of 10 or more. A large increase in drag is associated with an extensive region of supersonic flow over upper and lower surfaces of the airfoil, terminating in fairly strong normal shock waves. So, we find that gradually as you speed up the flow for an airfoil section, shocks start forming on the airfoil surface, and we are now concerned about how that shock would interact with the boundary layer which forms on the airfoil surface when we consider the viscous nature of the flow. As m infinity approaches unity, the flow on both top and bottom surfaces can be supersonic, both terminated by shock waves. For a reasonably thick airfoil, which are aerodynamically efficient at low speeds, when m infinity increases beyond drag divergence Mach number, the local Mach number can reach values of 1.2, 1.3 or higher. Therefore, the terminating shocks become stronger. These cause severe flow separation due to the adverse pressure gradient that they impose on the boundary layer, leading to a very important flow phenomena called shock wave boundary layer interaction. So, through the discussion we came to know how gradually shock formation on these aerodynamic surfaces can interact with the boundary layer and make it to separate. If separation occurs, then separation will be associated with drag rise. So, there is a large increase in drag, and why does that happen? Because shocks are associated with very adverse pressure gradients, and this is the reason why the boundary layer would separate. These shocks are comparatively weaker in the case of supercritical airfoils by virtue of their more optimized shape for such free stream Mach numbers. If m infinity is increased to slightly above unity, this shock pattern will move to the trailing edge of the airfoil, and a second shock wave appears upstream of the leading edge. Therefore, there is a detached bow shock formed ahead of the leading edge and there is a trailing edge shock. This kind of bow shock is also formed around bodies with blunted nose in supersonic and hypersonic flow regimes, which we have been discussing for quite some time. For high supersonic values of Mach number, of course, the shock wave is formed very close to the surface again, and the flow field between the shock and the body becomes very hot. This is the thin shock layer that we have learnt earlier in the course. The heat can be enough to dissociate or even ionize the gas, and thereby you get into the hypersonic regime. So, this is a continuous increase of free stream Mach number happening over a certain geometry and aerodynamic surface, and the consequent shock waves which form around the body, the aerodynamic and thermal implications of the same. That is what we have discussed, with particular emphasis on the idea of shock wave boundary layer interaction. Shock wave boundary layer interaction can potentially happen in different kinds of aerodynamic applications, starting from transonic airfoil to supersonic and hypersonic engine intakes, scramjet isolator around protrusions mounted on rockets and missile structures, in jet in cross flow arrangements for reaction control systems, fuel injection in scramjet combustor. As the moving shock sweeps through the shock tube, there will be shock wave boundary layer interaction. It can also happen in transonic blades of turbo machinery. So, there are a myriad applications where they occur, and we now have a quick look at the flow feature which accompanies this very important aerodynamic phenomena. This is a small sketch which indicates a typical shock boundary layer interaction. The discussion follows in the next slide, but before we go over to that, we recall rules of the wave reflection from a solid boundary and a constant pressure fluid boundary. Waves incident on a solid boundary reflect in like manner, waves incident on a constant pressure fluid boundary reflect in opposite manner. This is something that we have learnt in an earlier lecture, the previous lecture. So, you need to recall these facts when we discuss this phenomena. Shock wave boundary layer interaction is of course a fundamental phenomenon in gas dynamics observed in many applications we have already mentioned. Adverse pressure gradient across incident or normal oblique shock causes the boundary layer to separate on the body surface, and we can see a separation bubble formed here. The separation bubble acts as a ramp causing compression waves which coalesce to form an oblique separation shock. That is what you see over here. The interaction of incident shock and separation shock generates additional shocks called transmitted shocks. The transmitted shock penetrates the separated viscous flow up to the sonic line and is reflected as Prandtl-Meyer expansion wave. Because there is a near constant pressure in the bubble, this causes a deflection of the shear layer towards the wall, where it eventually reattaches. So, we see the Prandtl-Meyer expansion fan over here, and remember that all this is happening because you have a strong adverse pressure which has been brought down to the boundary layer through this incident shock. Again, another important fact that you should remember is that this incident shock will never make its way right up to the wall, because it is a viscous flow, and within the boundary layer the shock can propagate only up to the point where m is of the order of 1, slightly more than 1, and there is that sonic line which is lying embedded within the boundary layer, which says the shock should stop, it cannot propagate any further. Compression waves emanate from the reattachment location which coalesce to form the reattachment shock, and remember that below the sonic line the Mach number is less than 1, and therefore disturbances can propagate either way, upstream and downstream, and therefore the adverse pressure gradient information that is percolated right up to the wall, even through that subsonic region, would therefore propagate both upstream and downstream, thereby leading to information propagation about the presence of the shock. This does not happen, however, in the supersonic regime, where we know that upstream propagation of information is not going to happen. However, it happens through the subsonic regime. In many hypersonic vehicles, what happens is that these kind of shock boundary interactions can create a loss of performance. We now come to a discussion on hypersonic vehicles and their trajectories, and as we discuss it, we talk about the value of L by D max, which almost becomes constant above free stream Mach number of 2 for many such configurations. This is an example of Mach number independence. The value of L by D in general are low in the hypersonic regimes, generally not higher than 2.5 or 3. The comparatively low values of L by D are due to the increase in shock wave strength with increasing Mach number in the hypersonic regime, and hence the consequent increase in the wave drag on the vehicle. The L by D curve is rather flat over a large range of angle of attack. So, see, these are some of the general trends that we talk about. Keeping those in mind, we do a very brief discussion of hypersonic flight trajectories. Let us assume that a hypersonic vehicle is entering Earth's atmosphere from outer space. The high drag of the blunt configuration is beneficial in having high retardation. However, in recent times, hypersonic vehicles flying for extended times over extended distances within the sensible atmosphere are also on the rise. For these applications, improving aerodynamic efficiency has become an important design factor, along with minimizing aerodynamic heating, and aerodynamic efficiency is generally linked to lift to drag ratio. We earlier said that in most of the traditional designs, lift to drag has remained small. However, if you need to have extended periods over which hypersonic vehicles fly through the atmosphere, then you need to jack up the values of available lift to drag to make such configurations more efficient. The class of hypersonic vehicles that are boosted by rocket engines to high speed outside the sensible atmosphere and then they re-enter the atmosphere as glide vehicles are typical examples. So, we call them the hypersonic boost glide vehicles. The adjacent figure that we see over here shows the force diagram on such a vehicle which is performing a gliding entry, where L, D, W are lift, drag and weight. Theta is the angle between the flight path and the local horizontal. H is its altitude and R is the range it can make as it glides through the atmosphere. Summing forces and noticing that there is no thrust involved over here, forces parallel to the flight path give us this equation, while forces perpendicular to the flight path will give us the other equation involving weight and lift, with the sine and cosine terms associated with the resolution of forces. If you divide the two equations, you get this, and finally, you get an equation connecting the flight path angle and the L by D ratio. Notice that from the geometry, the altitude H and the range R clearly shows that shallower the angle theta, higher is the range R. The maximum range for the vehicle would be obtained when theta is minimum, and therefore, tan theta minimum would ensure that would simultaneously mean that you have a maximum value of L by D, and that also means that you will have the highest possible range. Therefore, from the range and altitude point of view, this is the way you explain it, that L by D max that you can manage helps you get to the maximum range. So, maximum range of a glide vehicle depends only on the maximum lift to drag ratio. Therefore, for a hypersonic entry glide vehicle, it needs to have as high a lift to drag ratio as possible. This is a result that applies from subsonic to hypersonic Mach number range. So, this is not a surprise really. Therefore, improving L by D max of course is an important finding which is reiterated here, and therefore, hypersonic vehicles which intend to glide for large distances would have to emphasize on improving the L by D max. If you talk about a hypersonic transport, a cruise aircraft, the propulsive aspect also comes into the picture. If you talk about the thrust specific fuel consumption and indicate it as CT, it is by definition the weight of fuel consumed per unit thrust produced by the engine per unit time. Its unit is per second, as you may recall. So, that goes by the units mentioned here. Let dW be the elemental change in weight of the airplane as it burns fuel, and over a time increment dt, therefore, the weight change dW can be indicated like this. Remember that a negative sign is included over here because with passage of time the weight reduces. Therefore, a positive dt is associated with a negative dW. You rearrange the equation and place it like this in terms of t, and then the incremental distance traveled by the aircraft over this time gives us ds, the expression for distance, and you essentially plug in this relation over here. So, you have the expression for ds, and then you integrate the above equation from s equal to 0, where the weight is the initial gross weight of the airplane, W 0 to s equal to r, where r is the range and the weight is W 1, which is essentially the fuel empty weight of the airplane. So, the range is worked out like this, and we assume steady level flight for this calculation, and therefore, thrust equals drag, weight equals lift, and we also express them in terms of the aerodynamic coefficients as far as drag and lift is concerned. In the integral over here, we have the two limits, where notice that W 0 is definitely larger than W 1. If we divide the two equations that we just wrote by balancing forces, we get this equation for T by W. So, we have an expression for T which we can think of replacing in this integral, and therefore, in this integral you finally substitute it and you get the integral like this. Further, you change the limits so that you can take care of this negative sign, and you have got the final expression for range. In this context, it may be worth noting that the range is clearly evident that the range can be maximized if you have a very large value of CL by CD. That means essentially a good L by D max, and we have wave rider designs which are well known for their high L by D max, which are capable of hypersonic cruise, X51A being one of them. We have a small picture over here. High lift to drag ratio for a hypersonic airplane is vital, as is evident from the above equation, because it maximizes range. Since it is a hypersonic vehicle, we expect V infinity to be large. Additionally, we need a very efficient propulsive device which manages to keep the CT low. Therefore, that also helps in augmenting the performance and increasing the range. Therefore, for long range hypersonic vehicles, we have to have all these achieved in addition to managing the aerodynamic heat problem. Handling aerodynamic heating and simultaneously achieving high lift to drag ratio is essential for long hypersonic cruise missions. This can also make hypersonic transport aircrafts in future a reality. With that note, we take this forward a little further. We will now examine the flight path of lifting and non-lifting hypersonic vehicles during aerodynamic or rather atmospheric entry from space, by also accounting for the centripetal acceleration effects. That means, when the vehicle is coming into the atmosphere and has a certain radius of curvature associated with its path. If you account for that, you talk about the centrifugal force maintains the radial equilibrium, and then the vehicle can fly stably with radius r during glide entry or ballistic entry. The ballistic entry is of course for a non-lifting entry, no lift or zero lift situation, unlike the cases which we just dealt with, where lift was a major consideration. In fact, that was way larger than at least larger than drag by a few times. We assume thrust to be 0, and then if you sum forces along the flight path, again using the same nomenclature, you can show that the equation works out like this. Summing forces perpendicular to the flight path, that is where centripetal force comes in, and r is the local radius of curvature of the flight path. For most entry conditions, the flight path angle is small, therefore, the sin theta can be assumed to be 0, cos theta 1. Further, mass can be expressed as W by g. So, if you put all those things together, you can actually show that we have got down to the drag expressed like this in the form of CD. So, W by CDS is defined as the ballistic parameter. It is clearly influencing the flight path of the entry vehicle via the solution of this equation. For a purely ballistic re-entry, in which case there is no lift, W by CDS is the only parameter governing the flight path for a given entry angle. So, this becomes the governing parameter, and this basically comes from this equation. And keep in mind that this equation would reduce to a simpler form like this when you apply these conditions. Expressing the lift in terms of the lift coefficient, again from the second equation you can show this, where W by CLS is the lift parameter. It clearly influences the flight path of a lifting entry vehicle by the solution of the above equation. Therefore, the above equations clearly illustrate that these two expressions are important for determining the flight path through the atmosphere of a vehicle returning from space. Such flight paths are plotted on a velocity altitude map. These maps are convenient diagrams to illustrate various aerothermodynamic regimes of supersonic and hypersonic flight. So, we learnt about the lifting and ballistic cases here, and now this is the last important thing before we close. We have a graph on the chemically reacting nature of air at different velocity altitudes. Various altitudes would also mean various pressures, and remember that if it is a reacting medium, then the reaction rates will depend on the pressure which are existing there at those altitudes, along with the temperatures which exist at those altitudes. So, it is a velocity altitude map with superimposed regions of vibrational excitation, dissociation of oxygen and nitrogen, and ionization of air. It also indicates typical flight trajectory or path of lifting entry vehicles. So, though it looks a little jumbled, try to see that along the x we have velocity in kilometers per second, along y height in kilometers, and then at velocities above 10-11 kilometers there is a possibility of ionization. This is the line which governs 10% of the medium ionizing, followed by a lower speed range where nitrogen dissociates, which are marked by these dashed lines. This is the region which is associated with nitrogen dissociation, the 10% and 90% completion limits. At a still lower velocity, the type of temperatures which are going to be produced on the vehicle creates oxygen dissociation, again marked with 10% and 90% limits, and at the lower end the vibrational excitation. Finally, the calorically perfect gas range, which lies below 1 kilometers per second velocity. Now, if you follow these curves indicate typical trajectories of lifting entry from Earth orbit. We have the parameter m by CLS, which we just learned. If you have of the order of 50, it follows a path like this, the one that you can see on top. If it follows m by CLS equal to 500, it will follow a path somewhat like this, and the dashed one may be corresponding to a particular vehicle which is entering the Earth's atmosphere, following a particular trajectory, lying within that band and having a suitable m by CLS value which suits that configuration. So, this plot gives you a feel of how velocity, altitude accompanied with the chemical reactions which occur in the medium can all be put together into a plot. So, we conclude by saying that in this lecture we completed the discussion on shock-shock interaction. We discussed about shock wave boundary layer interaction, that was followed by lifting and ballistic entry of hypersonic vehicles, and we further discussed at the end about hypersonic flight paths during atmospheric entry conditions through velocity altitude map. Thank you.